Hi everyone, welcome to this specially curated masterclass, which is part of NUS Open House 2022. We would like to remind you to please set your phone to silent to minimize any disruption. With that, we would like to welcome Dr. Sorain, whose masterclass will touch on the science and the scientific method of environmental studies. Dr. Sorain, please.
Hey, hi everyone. So welcome to the folks who joined us today. It's nice to see some faces. And hi to the folks joining us from Zoom and live stream as well. So my name is Sorain. You call me Dr. Sorain if you really want, but Sorain is fine. I'm a freshwater ecohydrologist. So I'm based in the geography department, where I teach environmental studies program. So alongside me, we've got Prof. Peter Todd and Zahida Hussain, who's going to be joining us from Zoom. And the three of us are going to be able to answer your questions towards the Q&A session right at the end. So what we're going to do today is have a bit of an introductory class on environmental studies. Okay, so the aim or the outline of today's talk is basically trying to introduce you folks to the terms of the wicked environmental problems. Okay, so broadly speaking, what are they? And just very briefly, we'll cover them. You'll have plenty of opportunities to learn through this process when you join BES. Okay, so when we see a variety of images or we hear about these environmental problems or environmental crises, we typically search out information. Okay, and in one of my methods modules, I really teach or I encourage students to really think critically about information. Where do we get that information? How do we look at this information? Right? What can we gather and glean from this information? It's not just about data, numerical data, but it also involves interview transcripts, social sciences, because tackling these environmental problems requires a holistic viewpoint. So what young people have in abundance is that passion. Okay, folks want to make a change to this, to like the issues that we face today, right? So in order to complement that passion, right, that passion to change the way we utilize our resources, okay, the way we interact with our environment. To complement that, I want to talk a little bit about the importance of empirical research data. And this is why it's important. In order to, passion is great for raising awareness. That's what we want to do. Right? We want to raise awareness about a particular problem, a particular issue. But when it comes to policy change, we need that empirical research data. We need to employ scientific methods, utilize scientific research to get that empirical data to then formulate policy, inform policy decisions. Now I'm going to focus the scientific method by using a case study that myself and former colleagues from biological sciences as well as geography have worked on, and it's the NUS freshwater swamp forest. And from then we'll sort of go broader again to think a little bit about how can we get that data to then come up with some of its focus management recommendations. So there will be some graphs and there will be some data, but again, it's not necessary to confuse folks or inundate you with a lot of data. In the module as well, the methods module as well as in the BES program, there are plenty of opportunities to do social science. But like I said, the data is completely different. Okay, here I'm just showing you the use of empirical research data and how we can then use that, complement that to try to affect management change itself. Okay, so what are wicked environmental problems? So here I've just extracted some images, right? That if you Google search some of these pertinent issues like climate change, you typically see like a lot of headlines from the UK talking about the issues of climate change and global warming and how we are running out of time essentially. And that's just a global example here. There are other issues as well, and you will typically hear about this in the module about how the wicked environmental problems transcends not just sort of transboundary, but also it can affect sort of individual countries and so on, where we've got Australia's freshwater scarcity is increasing, right? And that is exacerbated by climate change as well as poor human management. I think it's not just the environment that is driving this change, but it's also what we are doing to that particular resource. Okay, more and more we kind of come across plastic pollution, right? Folks who are, I mean, we put it all on TikTok rather than myself. But there are probably a lot of awareness being raised by Instagram, or TikTok, and so on, right? And we keep coming across these kind of plastic pollution headlines, okay, like how we need to basically have like a plastic bag ban or straws, ban and so on and so forth. And then closer to home, we've got news articles that are regularly published discussing about what are we going to do with our increasing waste. Okay, so our island is running out of space, and there's of course timelines in which we have to do something. But all of these problems have a couple of similarities. These are large-scale problems, okay? Global, regional problems. They are occurring over long time scales, right? They are compounding risks and uncertainties. And these risks and uncertainties, they undermine future growth, not just economic growth, but future growth, right? They are undermining resource security, right? How do we utilize such resources like fresh water, right? They are undermining regional stability because of these transboundary issues, such as global climate change, right? So these are huge problems that are taking place. Another similarity is that they are complex socio-environmental problems. So as I mentioned here, you've got land that is being mismanaged, okay, the watershed is mismanaged. So these are complex socio-environmental problems that require a holistic thinking. And we really have to change the way we think. So in the methods module, what I get folks to think about is that you have to train your mind to see the world differently. Okay, so whenever we see such pictures, like the headline I showed, and this rather provocative photo of this polar bear, and so ice caps melting, and so on, it raises awareness. And most of us will basically Google this, right? Or use our phones or use our laptops and so on. So we are now living in an information age. The way we access information, the way we share information has completely changed. The way we learn in the digital world has completely changed, right? So all of this can cause confusion over where the data or information come from, right? If you're confused over the source of the data, then that contributes to the problem of data validation. You don't really know who has come up with that particular data or information. So all of this kind of leads to a big problem, okay? How do you make proper assessment of that environmental change if you don't really know the source of the data or the source of the information that you are getting? So then who do we believe, right? Okay. And the way I kind of see this is that there are potentially 3 different types of views that helps us shape our understanding of that natural environment, right? So you've got the political view. So you've got folks like Donald Trump, former president of the United States, and he's very vocal about the topic of climate change. And here, this particular BBC image shows you a variety of quotes that is released or constantly tweeted, right? And many of them are basically he just doesn't believe in climate change, right? So, you know, that kind of view can shape our understanding. Another view is our personal view, right? So the way each of us experiences a change in temperatures can be very different, okay? And if I was to ask you, what was the weather like today? You can give me a pretty good, accurate, reasonably accurate representation of what it was like, hot, humid, etc., etc. But if I ask you folks to think back 5 years ago, and remember, working environmental problems are a long time, right? It's evolving over a long time scale. If I ask you folks to describe what the weather was like 5 years ago on a Saturday in March, most of us will not be able to remember or even tell it, give an accurate representation. Okay, so all of this can shape our view. So when we're thinking about these things, we are talking with friends, we are talking with colleagues over lunch, over dinner, whatever. We are sharing our views. All of us are susceptible to bias, okay? And we can influence other people in the way we share our personal information. And then the third way, or the third view, is the scientific view, right? Now, science is interesting because it aims to generate, or it's designed really to generate information, okay, that either approves or sort of refutes falsifiable hypotheses. And we basically use a variety of equipment. Here you can see like weather stations that are again built to obtain data sets over decades. So in this particular image here as well, so you've got basically science equipment that is used to collect sea surface temperatures, so as well as land temperatures. So all of these things, science is basically designed to collect this information in an organized manner. Oh, okay, sorry. Is that better now? Okay, sorry. Okay, I hope folks can hear me a bit better at home now. Okay, thanks. Sorry. So yeah, so we need to. Okay. So we need to think clearly about where do we get this particular information. So as I said, most of us will typically go and search things on Google. Okay, and each of us are very susceptible to biases. Okay. But search engines, they are the epitome of confirmation bias, right? You don't want to be using that you don't want to use that evidence to talk about whether you're right or wrong, right? And besides, it's not about being right or wrong. It's about being effective, right? So, is it the mic? There's that. Okay, so I hope that's better now. The challenges of Zoom. Okay, so we will, and we're trying to move towards like the scientific sources. Now, as I mentioned, right, scientific empiricism strives to be repeatable, it strives to be accumulable, and it's publicly observable. Okay, these are the things that we get from scientific sources, rather than, like I said, from Google, right? Those particular information, we don't know who's produced that particular information. So the thing is, what we try to encourage that kind of thinking in the methods modules is that, what does it mean to be skeptical? So again, to be skeptical about information, about data, but a proper skeptic questions what they are unsure of, right? But recognizes when valid evidence is presented. And they use this valid evidence to then change their mind about their thinking, right? We also talk about what does it mean to be convinced by data. So when you have data, we need to still critically analyze those data, critically think about those data, critically think about how it's collected and so on. So when we see this graph here, okay, where you've got the recent IPCC report on climate change, so this is a combination, the final report was a combination of 270 scientists or experts working over 3 years to come up with this graph and check on its model projections. Okay, so you've got that many experts working and double checking and ensuring that the data that comes out is as accurate as possible. Okay, so these are the things that we need to kind of think about science and the data that we get. Okay, so, and this is why there needs to be a change in the way we approach environmental problems. So many of the challenges, as I mentioned, they are complex. They're socio-environmental problems that are really complex. And as a result, we need a deeper understanding of a variety of spheres. So we've got the biophysical world, we've got the society sphere, and then we've got the technology as well. Okay, so this is where environmental studies and its methods comes in. Okay, it gives us an insight, it gives us a greater understanding of the theories, the methods, and the concepts between these spheres, the biophysical and society and the technology as well. But what's extra in environmental science is that we get to explore the interactions between them. They don't work in isolation, folks, right? They are working together. So there's a lot of interactions that take place that requires us to try to break down these different methods, try to break down these different interactions. So and then it gets us thinking, what type of strategies do we need to then tackle these wicked environmental problems? Right? You can't just tackle it by exploring the biophysical world. Right? You also have to think about it from a societal point of view, right? But there's no harm in trying to break it down first, and then but we also train you folks to think about it holistically. So environmental problems, the object of environmental sciences, is a combination of observations. So as I say, the observations that are taking place in our natural environment and the society, as well as the evaluation of observations. So why are certain things happening, right? What do they mean, and so on. So natural sciences and social sciences, they have distinctive languages and really distinctive methods. Okay, and they both produce very different data sets. One is very numerical. So again, this example of former BES students, or actually they're in year 4 now, about to graduate, last MSM, so to speak. They are basically sampling from a stream in Bukit Batok. And here the students are, before this, they were collecting some hydrochemistry data. So looking at pH, conductivities, and dissolved oxygen. And now, in this photo, they are using a train net, they're using a silver sampler. So the train net is basically used to collect fish, okay, and other larger insects, whilst the silver sampler, depending on the mesh, collects the smaller aquatic insects. Okay, so here you've got a combination of the hydrochemistry that's taking place And then you've got the ecology that's taking place. So how does the chemistry have an effect on your particular ecology? Okay. So here, in this picture on the right-hand side, again from BES Fillmore in Bohol, the Philippines, where the students were interviewing forest reserve managers. So again, in order to try to tackle these kind of problems, we need to understand the stakeholders, the role of the stakeholders, right? We want to know how they're using that particular resource. Okay, so here the students are basically trying to interview and try to gather some insights into the ecosystem services that are used by different stakeholders. So science is systematic, right? In order to do those two methods, the natural sciences as well as the social sciences, we need to think about systematically. Both are sciences. Yes, they produce different types of data, but the way we develop the methods is still very scientific, it's still very systematic. It's systematic in the way it organizes or shares, the way it builds and shares information, okay? So environmental scientists always, collect, analyze, and share information for a variety of reasons. And our objectives can then help formulate questions, which can then help formulate or design our research method, right? Our research design and so on. This is where we use the scientific method. Now, the scientific method really is a process where we use to find answers to questions about the functionality of the ecosystem. Okay? So, whilst the scientific method may have a certain number of steps, that number of steps varies depending on the type of question or the type, if you're applying it for the social sciences or the natural sciences part in itself. So the next part of the talk or the class is going to just be application of the scientific method on a case study. So this is a project that as I mentioned, a few of us were working on, the Nisun freshwater swamp forest. And basically I'll run through the scientific method using this case study. So it's broad, it broadly covers this case study or the scientific method, it covers some points, but again, it's not inundating you folks with the data in itself, but getting you folks thinking about how we should be thinking about empirical data to complement, right, conservation. So the focus on Nisun was basically driven by the fact that it's the last remaining freshwater, the largest freshwater swamp forest here in Singapore. Okay, it's located in the Central Catchment Nature Reserve, so around here, and it's pretty small. Okay, so this is part of the observations. So before we kind of think about questions, your research questions, you go out there to the site, you walk around, you observe these things. One of the things that I encourage, in fact, one of the first classes that we do in week 1, to go outside and walk around and we observe things, observe the environment, how is it functioning? The soil, is there a particular degradation area that's taking place? Why? Okay, the green buildings that are watered and so on, how efficient are they being watered and things like that as well. So it gets you folks trying to observe. So I'm going to very quickly take you through virtually through Nisun just by describing it. Okay, so Nisun is a swamp forest, which basically means it's very boggy, it's wet. So there are parts where you will sink. That's fun, right? You get muddy and so on. It's very slow flowing streams, right? It's very slow. It's not like rapids or anything like that. They're pretty small streams. There's a lot of this leaf litter. Okay, so fallen leaves. I have other photos again as I will show you as we go through. So there's a lot of leaf litter. It's wet all the time. It basically means the leaves that have fallen, they decompose, they break down very slowly. Okay? But as they break down, they are releasing these things called organic acids. So lemon, right, or lime, you cut that, and the organic acid in the lemon or lime is citric acid. Okay, when you eat an apple, okay, the organic acid in there is malic acid. Okay? So here, there are a variety of organic acids that are being released, and they are, they can be different, right, in terms of species and so on, but it's also very it differs, right? So you're getting this organic acids that are being flushed in. Another reason why Nisun is worth conserving, right? It supports two endemic crab species. So this Paraprofusca reticulata, which is the swamp forest crab, okay, we call it swamp forest crab, and it has an Ermengardia johnsoni, which is over here. Okay, so again, these are how important these species are to Singapore's natural heritage. Okay, these two species are found exclusively in Nisun. So if Nisun, if that forest was to go, we are losing a part of our natural heritage. Right? So it's to try to conserve these particular organisms, right? So it's not just the crabs that we find, right? We also have, a lot of freshwater fish species that are found in there as well. So these are the important species that we need to preserve. So some of the environmental problems that have taken place, okay, some more current environmental issues. So this is Singapore back in 1943. So at one point it was covered by dense forests, okay? And freshwater swamp forests basically covered about 74 kilometers square. And now, because of the change in the environment and the way mismanagement is taking place, that's about 1.3 kilometers square, right? So that's like about an insane amount. So 90% is basically being removed, right? So a couple of examples here. So we've got like Pandan here, okay, Pandan Forest, I guess, Forest Reserve here. Okay, so this was back in 43. So fast forward to 2022. So much of it now is basically replaced by the industrial parks in Geelong. And then those of you who are living around the lakeside area, and well, I guess Chinese garden, Japanese gardens or area. So much of this has been replaced, or freshwater swamp has been replaced by this kind of, by lakeside and basic development and so on, right? And in addition to the Pandan Reservoir, is basically also taking place over this swamp forest. So you've got this infilling that's happening. Another case study or another example is you've got the Mandai, the swamp forests are found in Mandai. Okay, so again, these have been infilled for our Lower Seletar Reservoir. So you've got changes happening. Those folks who are living in Yishun, this was once freshwater swamp forest. So again, we've lost a lot of swamp forests around. Okay, it's kind of wetlands. So these are the issues that happened in the past. What about some of the contemporary issues? One of the most contemporary issues that's affecting us is acid rain. Okay, so the thing is, rain pH, it varies, but typically they're acidic. Okay, usually it's like around 5.5 or lower, right? So the rain that falls in Singapore are typically acidic. Okay, but it varies because it depends where the cloud forms or the storms form. If they form towards the west, towards Jurong sort of area, the pH is typically more acidic. The chemistry is very, very different. Because if you think about it, what's out there? You've got the petrochemicals, right? Your industries and so on. If it forms above, like towards Malaysia and so on, like this cloud, that's again going to be very different because it's forming over land. So all the different pollutants and so on, it's just going to be very different. Sometimes it forms over oceans. So again, your chemistry is going to be very different. But it's all very typically acidic. Okay? By that range, the value changes. Right? So that's our question. Right? So we've been observing all these things, and we're now developing or formulating the question. And our project was basically to try to describe the stream chemistry response to rainfall events. So again, as I said, the pH varies, but we are trying to figure out, well, what is the chemistry from different rainfall events? We want to distinguish the biogeochemical processes that affects your low stream pH. Okay, so Nisun is generally acidic because of that organic acids, and you're getting acid rain, right? So how is it getting there? Okay, how is this low stream pH? Which pathways are flowing, right, are contributing to the low stream pH? And this is where I've also put this reference here to remind myself to basically talk about how this paper looked at about 787 odd papers that synthesized it, trying to figure out And one of the key conservation questions that they came up with, or they revealed, many of these papers basically lack empirical research. Right? If you want to make effective conservation policy decisions, we need some hard data, okay, to show these policy changes that are required. And that was another driver for us for this project. We want to systematically synthesize all the various drivers of acidification so that we can then think about, right, how do we manage them in the future. So by understanding environmental change, we were trying to protect and conserve the star of the show, the celebrity amongst us, the swamp crab, okay, the first swamp crab. So from that, we can then propose implementation plans. We can then propose, some kind of policies to try to secure certain portions of the habitat. So how do we go about trying to collect the data? So we used a variety of techniques. Okay, so these are all part of hydrology and hydrochemistry. This is a combination of two different disciplines, right? So we collected rainfall. So again, as I said, depending on where the storm was coming, it can change chemistry. So we had two of these rainfall gauges. So one near NUS, because we wanted to see, well, if it's coming from twice, and we looked at a variety of basically maps really to try to figure out what point basically there is, in particular when the rain was coming in. We also had another rainfall collector in Bukit Timah Nature Reserve, okay, something close to this site. We collected soil. Okay, so these are the leaf litter. So it's very swampy. Okay, so it's very boggy, so it can sink. So we looked at the soil. So we're taking, again, a lot of physical geography is what taking place. Yeah? So we took a soil core and wanted to see, well, how does it change from the surface all the way down to about, it ranged between 1.5 to 2 meters. Okay, so towards the surface it's darker. So this is because you've got a lot of this leaf litter, a lot of this decomposition happening. But as you move down, it's getting a bit lighter, so you can see. So there's a change in soil there, right? And again, I'm not necessarily going to show you all the results because again, we don't really have the time, and of course, there's a lot of data. Right? We also have this monitoring station. Okay, so this monitoring station was set up to collect basically data at 5 minutes resolution. But when it rains, it triggers, so it goes to like about a minute. Okay, every minute it's recording data. So that's something we cannot humanly do. So we need help from technology. Right? And this monitoring station has connectivity, has pH, has dissolved oxygen, right? And a water level sensor as well. So when it rains, the water is going to go up. So we want to see, make sure that everything is working, right? So we all have that. So how does your chemistry change as the water level rises with more rain? Does it get more acidic? Does it get less acidic? What's happening, right? We also have these groundwater wells. Okay, so what's happening to the water in the soil system? Is there some kind of buffering that's taking place within this ecosystem? Okay, but what's actually happening? So we're trying to work out these neutralizing capacities and so on with all of the samples. So now that you know how we collected our data, let's have a very brief look at what our data showed. Okay, so there's a lot of points here, so I don't necessarily want you folks to fully focus on everything that's going on. But again, this is just to show you an insight of what empirical research data can show us. Okay, so these are your rainfall chemistry that was taken in the NUS. So notice how acidic the pH, how strongly acidic this pH are versus some of the others that were taken from Bukit Timah Nature Reserve, right? So again, while their range is different, as I mentioned at the start, they are typically acidic. Okay, so it's below the 7, right? So they're typically acidic. So have a look then at like the stream chemistry values. So they're typically a little bit, less weakly acidic, right? And it also shows that there's some buffering. So acid neutralizing capacity tells us the ability of basically neutralizing capacity, really, how strongly neutralization takes place. So there are some neutralization taking place, but not a lot. Again, with the groundwater, right? So again, there's some neutralization taking place, but perhaps perhaps it's not as strong, right? So poor buffering. So you can see that across the different streams, and even in some instances, there are, small differences in there. So even within short distances, you are getting different niches or basically small nuances within how a catchment, works and how it utilizes or how it basically changes the incoming rainfall. Another way in which we can look at this is basically, again, I've extracted just 2 storm events just for the purpose of today. But again, this paper in particular, if you're interested, it's free to download. You can have a look, and there's basically like a year's worth of data, right? A year and a half, to be honest. And here, after a rainfall event, you can see how the pH drops, and it's just not for one stream. So 3 of our gauge stations are showing this huge drop, okay, after a rainfall event. It's a huge drop there. Okay, and it's not just, like I said, within the 3 streams, it's happening at different storm events as well. We get an idea of how the conductivity, specifically electrical conductivity, is also changing. So some lab work that we did, we took soil cores and we poured stream water, and we wanted to look at how much ions are basically released, and we found a lot of potassium that's being leached out. So this is driving, so you've got positive charge, and that's driving all your specific electrical conductivity up. So that suggested to you sediment is being washed in. Okay, when sediment is being washed in, it has a lot less potassium within the soil matrix in itself, and our leaching experiments that we did as well adds into the story. But just to communicate that results, just to conclude that story and the paper and so on, is that we came up with this conceptual diagram, okay, where trying to understand the pathways is very complex. It takes place over multiple sort of scales, basically. And that's the thing about the environment, right? It happens in a complex way. Things are functioning in a very, very complex manner, and we try to disentangle this, gather an understanding. And what we found is basically these acid events are typically, it's a natural phenomenon because Singapore gets a lot of acid rain. But these decreases in pH are typically related to acid rain, as well as these organic acids that's being flushed in. Okay, and you can see that in the results as well, as I mentioned. But these really big drops in pH, right, when it becomes really strongly acidic, that is more likely to be amplified by sort of this sulfur and NOx species. So for now, like these events, so you can see the drop in pH is pretty short-lived. Within less than 24 hours, it's getting back to normal, right? It's basically it's reaching to the normal stage. But if you read a lot about the subject, you know that modeling studies, just like how the initial graph that I showed you about temperature, a lot of modeling studies shows that urbanization is going to increase. You may have gone to Shantino's earlier talk, and he was talking about urbanization. Urbanization is expected to increase, and alongside, you're going to get, a lot of industrialization. You're going to have an increase in vehicles as well. So all this is going to increase the emissions of your sulfur and your NOx, and nitrate species as well. So what does the future hold for this particular environment? So there's always going to be a trade-off, okay? And we need to think about how, if we're trying to conserve and protect management and so on, there will be, of course, some trade-offs. We can try to protect everything we can, but of course, we need to think realistically as well. And what the challenge really is trying to learn as much as we can about the system. So our recommendation or suggestion to NParks is basically, trying to think a little bit more about what core species or zones or habitats can we conserve. Okay, so these are the things that we need to think about. Again, I'm not necessarily going to divulge or talk about it here because we're lacking in time, but these are the things, which core habitats do we really need to conserve, to protect and conserve our natural heritage, right? So, and the couple of take-home messages is that, the combination of these transdisciplinary methods has enabled us to gather some further insights. So So these are the things that BES students do, right? Trying to understand or have a go at transdisciplinary methods. And this is one way towards conservation planning and empirical research data. So yes, we did it in USU, but this is also applicable for other nature reserve, like Bukit Nature Reserve. So within there, you get another rare endangered species, the Geomorphology, right? So again, these are part, and that's also, something else that we need to conserve. So just to go back to the final kind of slides, long-term, these wicked environmental problems, they are long-term, large-scale problems, and we need to basically develop skills, or we are teaching skills in which you folks can think holistically and think in a transdisciplinary way to address some of these complex problems. So what strategies are basically needed to tackle these wicked environmental problems? Well, there are no unique solutions, okay, to tackle these problems. What it simply means is that we need your passion. Okay? You folks are passionate about the environment. So we need that passion, and we want to, with BES, we join BES, we want to harness that passion, okay, towards developing you folks into environmental scientists to tackle some of these problems and come up with solutions. So final slide with acknowledgements. I would like to thank, so a lot of BES students were involved in the project, okay, as well as geography students. So these are some of them. You've got like a variety of folks doing honors theses, independent studies modules, masters. And last but not least, I also want to thank Prof. Alan Ziegler over there, who basically was instrumental in basically developing the project and moving forward and mentoring and so on as well. So thank you very much. We are running out of time, right? Okay, thank you.
Thank you, Dr. Sorain. To open the floor for any questions you may have, and please keep them content related. You may use the mics at either out. And Zoom participants, please post your questions on the Q&A or chat function. Okay, any questions, please?
So you folks can ask questions about the program as well. Interesting. Sure, yeah, go ahead.
Sorry. So a lot of social sciences have problems in reproducibility, like internal of like information. How do you think environmental sciences have like overstepped these issues, and why is it about the nature of environmental sciences that allow these solutions to come, that allow this sidestepping of issues to be possible?
Okay, so in terms of reproducibility, it's the same. It's so with social sciences. So again, I also teach a little bit of social sciences, but some of the experts are also based in geography that folks can, if you enroll in environmental studies, you also take some specific environmental social methods as well as modules. And the issue with reproducibility is that you are having a larger representation of people that you're interviewing. So it's not necessarily, and within that, you have different stakeholders. So you wouldn't just go to one particular fisherman and you wouldn't just like interview that one particular fisherman. So this is how we are trying to basically have replicability. So you're trying to gather as much insights about a particular service. If it's a marine area, let's just use an example. So you want to gather as much insights from your fishermen, your tourist groups, because for diving purposes, for snorkeling. What about the enforcement, right? Because you also want to try to conserve that marine protected area. So you definitely want to gather as many interviews as you can from those, just for example, like just 3 stakeholders, right? There are other stakeholders as well. And that's what we do as well in the Philippines. We go through on the field mod. We are talking with different stakeholders and different numbers, right? The difference here with environmental sciences is also because we're collecting the physical data in addition. Okay, so you are also versed in social sciences, and no disrespect to social scientists at all or anything like that. So full disclosure. It's different in the sense that it's more theoretical, okay, and basically there's a lot more interviews and ethnography involved. Again, but no disrespect basically. It's just different. It's just different methods. I feel.
Any other questions?
It's not to say one is better than the other, but we need complementary. That's basically what it is. And we need to see that they complement each other a lot.
There are no further questions. Once again, thank you, Dr. Sorain. We have come to the end of this session. If you have pre-registered for the walking tour, please head out to the tour booth outside LT11 to begin your tour. Due to safe management measures, we have limited capacity for these tours and only accept pre-sign-ups. However, feel free to take a walk around our campus or take a shuttle bus to U-Town and take part in the other activities throughout the day. Thank you and have a good day in the NUS.